And hi to all of you. Right, so today we will continue for chapter 8, part 2. Okay, chapter 8, part 2. Alright, okay, so chapter 8, part 2. So in chapter 1, can someone tell me what equation that you derive for, not chapter 1, sorry, chapter 8, part 1. What is the name for the equation that you learn to derive? Anyone? Iqbal, what equation that you derive in chapter 8, part 1? Iqbal, Iqbal.
Poisson's equation.
Poisson. Hagen-Poisson equation. Okay. Thank you, Irfan, for your answer. Okay, so that one is quite an important, okay, derivation. Okay. I think the step is not quite confusing. The step is quite straightforward. Just the step is quite long lah. Okay. But if you focus and you write back, inshallah you will understand on how to derive the Hagen-Poisson equation. Okay. Alright, so in chapter 8, part 2, okay, so for Hagen-Poisson, it only applies for laminar flow. Okay, laminar flow. So in chapter 8, part 2, we want to focus on turbulent flow. Not clear. Okay, turbulent flow. Alright. Okay, so as usual, before we start learning, I will give some motivational quote. Okay, as you can see here, difficult road build skillful drivers. Okay, difficult wheels will build perfect sailor. So we can conclude that in a difficult situation, it will build strong people. So do you agree with me? Come on, guys, some respond.
Yes, madam.
Yes. Okay. Alright, so difficult situation will build a strong people. Okay, so please remember this. Alright, so we move on to our main agenda. So the objective for this chapter 8 part 2 is to acquire fundamental of characteristic of turbulent flow. Okay, the keyword is turbulent flow. For chapter 8 part 1, laminar flow. Okay, so there are 4 learning outcomes in this chapter. So for the first one, you will learn on how to calculate pressure drop. Okay, delta P is pressure drop. Second, calculate head loss. Okay, calculate head loss due to friction, HF. Okay, H small f, using Darcy-Weisbach equation. Third, to determine friction factor, or we denote as small f. Okay, friction factor. Friction factor from Multichart. Okay, later I will teach you on how you can get friction factor from Multichart. The last one is to calculate relative roughness. Okay. Alright, so we go straight forward. The friction factor formula. Okay, so for a horizontal pipe, okay, horizontal configuration, the formula is, okay, so delta P is pressure drop, right? Okay, pressure drop is equal to, so F is friction factor, okay, small f is friction factor, or it can be termed as Darcy friction factor. Okay, so this symbol is absolute roughness of pipe wall So if you divide absolute roughness with diameter, you will get relative roughness. Okay, so be careful if question give you absolute roughness, so you must change to relative roughness by dividing it with diameter. Okay, so this one is equation for pressure drop, and this one is equation for friction factor. Okay. Okay, so as you can see, friction factor will be depend on Reynolds number and relative roughness. Okay, relative roughness. Okay, so as I said before, be careful. Okay, if question only give you this absolute roughness, so you should divide it with diameter, okay, to change it to relative roughness in order for you to get a correct friction factor. Okay. Okay, so the energy equation for steady incompressible flow. Okay. So can anyone tell me what is this equation? What is the name for this equation? Without HF first, what is the name for this equation? You have used this equation a lot, right?
Bernoulli,
Anyone?
madam. Bernoulli.
Yeah, Bernoulli. Okay, I can see. Who's give me the answer? Ifan, eh?
Yes, madam.
Okay. Alright, thank you, Ifan. Okay, so this is Bernoulli equation, okay? Please remember this equation, okay? This is, I can say as a heart, okay? A heart in fluid mechanics, okay? Very important equation, right? Okay, so before this, you have only learned this equation without HF, okay? So HF is friction factor. So in this chapter 8, part 2, you have to consider head loss due to friction. Okay, you have to consider head loss due to friction. So that's why we have to add HF into the Bernoulli equation. Okay, because we cannot neglect the head loss due to friction in turbulent flow. Okay. Okay, so you can see here HF is head loss caused by friction. Okay, so with assumption of a constant diameter, so we assume the diameter is the same, okay, so that this one is not volume, okay, don't confuse, it's actually velocity, okay, V equal to velocity, so velocity 1 will equal to velocity 2. Alright, so you will get delta P is equal to P1 minus P2 rho G HF. Right? So this is the equation. Okay, HF is equal to FL over D V squared over 2G. This is the Darcy-Weisbach equation. So it is valid for any fully developed, steady, incompressible pipe flow. Okay. So whether the pipe is horizontal or inclined, you can use Darcy-Weisbach equation. Okay. So later I will teach you, okay, on how to apply this equation. Okay, we have example at the last of the slide. Right. So in general, with velocity 1 equal to velocity 2, okay, the energy equation give, okay, so how you get this one? So it's actually like this, okay. So write back the Bernoulli equation, P1 over rho G plus V1 squared over 2G plus Z1 equal to P2 over rho G plus V2 squared over 2G plus Z2, and don't forget plus HF. Okay, so since we consider our pipe is in horizontal, so there is no inclination, so Z1 and Z2 we consider it as 0. Okay, but in case if there is elevation or inclined pipe, so we have to consider Z1 and Z2. Okay, so can I, it's okay, I just write back. Okay, so actually for velocity, okay, for velocity we can neglect, okay, because we assume that velocity 1 will equal to velocity 2. Okay, so we consider Z1 and Z2 in the case of inclined pipe. Okay, Z2 plus HF. So this one we omit lah. Okay. Then P1 over rho G minus P2, we try to simplify the equation. Okay, equal to Z2 minus Z1 plus HF. Okay, then we simplify more, P1 minus P2. So this rho G we bring to the right side. So we get rho G Z2 minus Z1 plus rho G HF. Okay, so this is how you get this equation. Okay, so P1 minus P2 is delta P lah, right? Delta P pressure drop. Okay, so then this one, how you get this one is, okay, you insert the friction factor equation, HF here. HF here you substitute with this Darcy-Weisbach equation. Okay, so you substitute this HF, okay, in this HF, then you will get this equation. Okay, I will write for you. Okay, so P1 minus P2 equal to rho G Z2 minus Z1 plus rho G. Okay, so you substitute F L over D V squared over 2G. Okay, so since we have G here and also here, so we can omit, okay, G. So we just left with P1 minus P2 equal to rho G Z2 minus Z1 plus F L over D. Okay, this row, okay, this row I just bring here, okay, rho V squared over 2. So this is how you get this equation. Okay, understand guys? Is it okay?
Yes, madam.
Okay, alright, thanks for your response. Okay, so this is our main, okay, main topic lah, main agenda, Multichart. Okay, so actually from Multichart you can get friction factor, the small f. Okay, I show you how the Multichart looks like. Alright, so this is the Multichart. You can see the y-axis is small f, friction factor. Okay, so at the axis you have Reynolds number. Okay, and this one you have relative roughness. Okay, so that's why I ask you to be careful. Don't simply use absolute roughness. Maybe sometimes the question trick you. It give you only absolute roughness. Okay, if you don't change, so you will get a wrong friction factor. So make sure you divide absolute roughness with diameter. If the question directly give you relative roughness, so you can directly use, okay, relative roughness. Okay, so this is basically what Multichart have. Okay, in the chart you will have Reynolds number, so you will have to calculate the Reynolds number. Okay, then you will have your relative roughness, then you will get your friction factor. Okay, later I show you when we solve the example. Right? So from Multichart, okay, for laminar flow, okay, for laminar flow, you can see that it depends on Reynolds number. Okay, depend on Reynolds number, but it is independent of relative roughness. Okay, relative roughness. For very high Reynolds, okay, for very high Reynolds means turbulent, right? Okay, it is depend on relative roughness. Okay, it depend on relative roughness. Depend on relative roughness, but it is independent of Reynolds number. Okay. Alright, so we want to do this exercise, okay, in order for you to learn on how to use Multichart. Okay. So calculate the loss of head. Okay, calculate the loss of head due to friction. Okay, means that you have to calculate HF. Okay, head loss due to friction HF in a horizontal circular pipe of 40 millimeter diameter and 750 meter long. Okay, when water, so is given the dynamic viscosity, okay, mu, flows at a rate 4 liters per minute and 200 liters per minute. So pipe relative roughness is 0.002. Okay, so the question already give you relative roughness, right? Okay, so you can directly use. But if the question given you absolute, so you must divide with diameter. Okay. So in order for you to use this Multichart, okay, in order for you to use this Multichart, so you have to calculate Reynolds number first. Okay, so before that, okay, so you know that you have to calculate HF, right? So you write first the equation for HF, F L over D, V squared over 2G. Okay, so if you write the equation, so you can know what info you should have, okay, or you should find in order for you to find HF. So you have to find friction factor. Okay, so friction factor, how you want to find? So it is from Multichart. Multichart. Okay. So length, the question already gave to you, right? 750, diameter also you have, right? G is your gravitational force, okay? So as usual, 9.81. Then V squared you can calculate, okay? So first step, you have to calculate Reynolds number. Okay, so Reynolds number equal to rho U D over mu. Okay, so this one you have learned in chapter 3, right? Okay, Reynolds number. Okay, so you should also know that flow rate is equal to velocity times area. Right, so you can find velocity U by dividing flow rate with area. Okay, then substitute this U into this one. Okay, rho, so U equal to Q over A, right? So Q, I put A below. Okay, Q over A equal to U, then you have D and you have mu. Okay, so rho QD, then mu, so area of a pipe, pi d squared over 4, right? Okay, so then you bring this 4 here, so you will get 4 rho QD over mu pi d squared. Okay, so you can omit this t. Okay, so you just left with 4 rho q over mu pi d. Right, so plug in all info that you have. Okay, so water, right? Okay, so who knows density of water? Raw water. Anyone remember?
1000.
Yeah.
1000.
1000. Alright, thank you. Okay, so raw water is 1000. Okay, so 1000. So for the flow rate, 4 liters per minute, okay, you have to make sure that the unit is uniform, okay? So you must change the unit into meter cube per second, okay? So for, okay, you have to divide with 1000 and 60 seconds, okay? In order for you to get 4 liters per minute in meter cube per second. Okay, then divide with mu, okay, 1.14, okay, 1.14 pi d diameter, okay. So 40 mm, make sure change into meter, so you will get 0.04 meter, okay. Okay, so when you calculate this, you will get your Reynolds number is 1861.4613. So if this Reynolds number, so it is laminar, transition or turbulent flow? 1861. Below 2000. What type of flow?
Laminar.
Laminar. Okay, good. Okay, so laminar flow. Alright, so we already get the Reynolds number, and we also know the pipe relative roughness, so we can use the Multichart in order to find friction factor. Okay. Alright. So this one correspond to your Reynolds number, relative roughness, and friction factor. Okay, so we focus first on Reynolds number. Okay. So your Reynolds number is 1861, right? Okay, 1861. So it is here, okay, in between, okay, in between 1.5 and 1.9. Okay, so don't confuse because the unit is in 10 to the power of 3. Okay, so this one mean 1000 lah. Okay, so 1861 is around here. Okay, so you just drag, okay, you just drag the line. Okay, okay, then you will get your friction factor here, 0.0338. Okay, okay, wait. Your friction factor, transition laminar flow, okay, F 0.0338. Okay, so okay, I write first. F is equal to 0.0338. Okay, so you can plug in your all info that you have in this equation. Okay, then you will get your HF is equal to 0.1022 meter. Okay, wait. Okay, this one example, okay. if you settle for example B. Okay, this one. Okay, later you can try to do it. Okay, exercise B. Okay, I just want to show you how you get the friction factor. I cannot see. Okay, so it's around 9.3 times 10 to the power of 4. Okay, 9.3 to the power of 4. So your your relative roughness is 0.002, right? Okay, your relative roughness is 0. Okay, so the difference is if for turbulent, you have to consider relative roughness. Okay, so you get, okay, I make it full slide back. Okay. Okay. All right, so your Reynolds number is around here, okay? 9.3, sorry, 9.3 times 10 to the power of 4, okay? So then you just drag the line, okay, until it touch this relative roughness line, okay? So you choose the one with 0.002, okay? Can see here, 0.0002, so this is the line. Then, okay, then from the intersection of your Reynolds number and your relative roughness, okay, you draw a line to the y-axis friction factor, so you will get the friction factor 0.0252. Okay, for laminar flow, okay. Okay, laminar flow. Okay, for laminar flow, you can see that it will not touch the relative roughness. Okay, so that's why, for laminar flow, you can see that it says that it is independent of relative roughness. So for laminar flow, it just depends on Reynolds number. Okay. But for turbulent, it is independent of Reynolds, but it depends on relative roughness. Okay, so that's why it's quite different on how you want to read the Multichart in case of lamina. Okay, lamina is here. In case of lamina and in case of turbulent. Okay. Right, so for laminar flow, you just draw a line until it touch this line, okay? Until it touch this line. Okay, so it touch here, right? Okay. So the point that it touch the line, then you draw a line to the y-axis, so you will get the friction factor. So here is around 0.0338. Okay, then you can put the friction factor formula into this equation. So you will get head loss due to friction. Okay, so for exercise B, I want you to try by yourself. Okay, whether you get or not. Okay, the answer, right? Okay. I think this one is quite straightforward and not too difficult, right? So any question, guys? Actually, we have finished for chapter 8, part 2. Okay? So if you have any question, you can ask, or no question at this moment.
No question yet, madam.
Okay, so later when you do your exercise or any question from final assessment, maybe you will have question, right? Okay. So I think that's all. Oh, wait, I want to download attendance list.